Hey guys, in today's video we're going to be covering section 1.2 in the Larson and Edwards calculus textbook, which is finding limits graphically and numerically. So let's begin. To begin with, it's important to establish a basic definition of a limit, and so one of the more common definitions is the one I've listed up here, which just states that a limit exists if and only if the graph or function approaches the same y value from the left and right. And so when we're dealing with limits, we have to understand that they are going to commonly occur in situations in which when you actually have a value, an x-coordinate, that you're inputting into a function or graph, you're going to find that that value, that y value that comes out might be unknown. And so what a limit tries to do is it actually tries to use the points that are known, that are very close to the unknown position that you're looking at, in order to try and figure out and determine what that missing function value in fact is. So we're going to do a couple examples here just to really illustrate that point. And so as this section is titled, we're going to be looking at limits from a numerical and graphical standpoint. And so to be completely honest with you, from a numerical standpoint, it'll be not as interesting as the graphical ones. It's going to be a bit more cumbersome, but these are both important things to cover nonetheless. So let's begin. So to begin with, we have question number 3 in our textbook. And this is going to ask us, we have the limit as x is going to 0. And this is a pretty common one. It's often common that when we're dealing with limits, we're actually going to be going to 0. And the function that we're dealing with is x plus 1 under the square root minus 1 all over x. So this is basically the function that we have, and we're trying to figure out when we input 0 in for x, what y value, what corresponding y value are we going to obtain. And the reason why this is a bit difficult is, as you can see, if you were to put 0 into this, right now you'd get a value of 0 over 0, and obviously that would be undefined. But the goal of a limit is that we can use values very close to 0, both above and below, such that by looking at their y values, we're able to figure out the y value when x goes to 0. So the thing with this question is the book actually provides us with our table of values. So we have, just going to make a quick table here, or chart. So we have x and we have f of x. So this is always going to be like this. And we're given from the textbook negative 0.1 as our first value. Our next value is negative 0.01. Then we reach negative 0.001. Then we finally make it out to 0, which is what we're trying to find. And then after that, we're going to end up going into 0.001. And we're going to reach 0.01, and then finally we're going to end this off by going all the way out to 0.1. And so, as you might notice, I'm going to point a couple of things out with this chart. To begin with, this chart that the book provides is pretty good, in the sense that the farthest that we get away from 0, both greater than and less than, is both 0.1. So we get 0.1 less than 0 and we get 0.1 greater than 0. And that's good because we want to have this symmetry, just because when we look at the function values, it then makes it easier to really draw conclusions as to what the value is, to what the value is approaching when we reach 0. But the one criticism I have of this chart is going out here and having 3 points above and below. I think it's a little excessive. Generally, just stick to 2 points, and then you should be good. But for the sake of the problem and what it's asking us to do, we will use all of these points that they've provided with us. So to begin with, the way we're going to solve this problem is we're going to just look at the function at each of these points that we're given. So we're going to look at we're going to look at the function when we go to negative 0.1. So all that we're going to have is we're going to have the square root, and we're going to put negative 0.1 in here for x, plus 1, minus 1. And then we have x again, so we're going to put negative 0.1 back in. And then all we got to do is we just got to simplify. And this is the part that is a bit tricky. And for this type of problem, you're definitely going to have to use your calculator. I have the calculations already all figured out here. So this is 0.05132. And generally, I like carrying these out to 5 decimal places for these problems just because we really want to have a lot of good certainty and have a definite answer as to what 0 is approaching. So carrying out to those decimal places definitely won't hurt you. Divided by negative 0.1, and then if we do the simplification once more, we end up getting that our final answer is 0.51317. So this is our first little clue here as to figuring out what this function is going to be at 0. So now we're just going to do the next one. So this, as I mentioned before, is a little bit cumbersome. Just going to have to plug and chug. And it's, thankfully not that hard. Just a little laborious, but that's all. Won't kill you. So we do this as we have done previously. And on the top, we get our numerator is negative 0.00501 all over negative 0.01. So we end up getting that at negative 0.01, our function's at 0.50126. So there we go. There's our next clue. We still can't really draw any conclusions yet as to what it might be at 0, but hey, at least we do have some points plotted that we can refer back to. So now we're at negative 0.001, and this, in fact, is going to be the same thing, just plugging and chugging. That's all we're doing. Plus 1, minus 1, all over negative 0.001. So we do this, we do our simplification, and we get that in our numerator we have a value of negative 0.00050 all over negative 0.001. Now I'm going to quickly point out that these values are all rounded. The numerators in this case, all 3 times, are rounded to 5 decimal places. And this value here, there's some residue, is what I like to call it, those additional values that come after this point here. There's some residue at the end, so actually when we divide this out, we're not going to get like a perfect value just because there is some leftover residue that's going to come up. So when we actually do the division here, we end up getting 0.50013. So here we go, we got our third clue. So this is looking good. We've established every single point that we want below. That's less than what we're actually looking for. So this is looking good right now. And just scroll the page a bit, and we're now going to actually look and try and see if maybe we can use this strategy to find 0, because that's what we're looking for. And what you're going to notice is that when we actually try doing this, as I did mention previously, it's not going to work. We're going to end up getting that this actually ends up being on the top 0 over 0, and that's a bit of a problem because we're not allowed to divide by 0. That's one of those rules in math that is just true and true, that we cannot divide by 0. Division by 0 is an error in math. It leads to a value that's unknown. So technically, the function at 0, if on the test they asked you, in this situation with this function, is f of 0, what value is it? You'd say it's unknown. You'd say it cannot be determined, because it can't. It's unknown. But that doesn't stop us because we're looking for the limit. We're not looking just for the function value, we're looking for the limit to try and see if this value did exist, what would it be? So then we're going to carry on here, and we're going to do 0.001. So now we're just working the other way, in the sense of we're now just looking at values that are greater than 0, and we're going to do this division again, 0.001, like this, and we're going to get, in this situation, we're going to get that the value of our numerator is going to be 0.00050 all over 0.001, we do our division, and we get an answer that is 0.49988. Now at this point, this is really good. We're in a good spot because we have values that are greater than, and we have one value that's less than our target value of 0. And so just from this, you could likely tell that our answer is going to be 1/2. If you look from the left, we're approaching 1/2. And if you look from the right, yeah, we're also approaching 1/2. 1/2 is right in the middle between these two values. So you could say pretty much with certainty that we are going to be at 1/2 as the limit as x goes to 0. However, we still got to carry on and do a couple more calculations. So I'm going to do those right now. So we have f of 0.01 that we got to carry out. So if we do this, we have 0.01 like this, plus 1, and then minus 1, all over 0.01. And there we go. So just hang on with me here. And we're going to end up getting a value of 0.00499. Make these a bit cleaner. All over 0.01. So there we go. And this ends up giving us a value of 0.49876. So we can pretty much say that so far we're doing pretty well. And one of the things to note is that when you're doing these types of questions, because you're so close, because each value of x is very close to one another, you really want to make sure that if you're dealing with a function like this in particular, that we didn't randomly say have a value of like 0.75 here. That wouldn't make any sense. So it's good to just use basic logic to kind of figure out if the values that you're obtaining are actually going to be correct. So then we're going to do this one last time, and we're going to see what we end up getting here. We end up getting, for this situation, we get 0.04881 all over 0.1. And so f of 0.1, as a matter of fact, ends up getting us 0.48809. So there we go. This is our final little piece of the puzzle that we got. And I'm going to scroll this up a bit so we can see our two closest values. Yeah, we can see all of them. We can tell that here we're at 0.50013, here we're at 0.49988. We can tell that, if we look at where these two values are approaching, it definitely seems that f of 0, or the limit, I should say, as x goes to 0, would in fact be 1/2. So that should be our answer, 1/2. That looks like that's going to be our answer. So there we go, 1/2. So one thing to point out too is, I hope I haven't made this mistake too often yet, but the function at 0 is unknown, but the limit at 0 is 1/2. So that's just one of those things. I know it's kind of tricky how it is, but it's sort of like how every square is a rectangle, but not every rectangle is a square. So just to be clear on that, hopefully I didn't confuse anybody, but let's move on to our next question. Okay, so the next one we're going to do is actually, we're going to stick to and go on to number 7. And so the difference with this question actually is the fact that this time around the book is giving us the discretion when it comes to determining the table or chart that we're going to use to determine the limit as x goes to 1. So we got to be a bit smart with this. And I'm just going to tell you some couple tricks that I like to use when doing this. So the first one is, you really want to choose values that are very close to 1 here. And as I mentioned previously, you want to make sure that you have some symmetry in that, the greatest value away from 1 that's greater than it, you want to be equal to the greatest value away from 1 that's less than it. So I'm starting off with 0.9, and we're going to go to 0.99. And then we're actually going to not add any more values below 1. We're just going to go to 1, because I think there's no need to do 3 values below 1 and 3 values above 1. That's a little excessive. And then we have 1.01, and then we're going to cap it off by doing 1.1. So there we go. So this is our table that we're going to use, and this is going to help us. So just going to do the same process as before. The only difference was this time we had discretion over the table. And just going to fill in, replace every time we see x with our function value that we're inputting. And then we're going to do this, like this. If I could draw, that would be nice. And this is going to end up giving us, if you're wondering, we're going to get negative 1.1 all over on the bottom, negative 4.29. So this all simplifies. God, why are my 9s so bad? I don't know. This all simplifies down to 0.25641. So there we go. This is our first clue. We don't know too much yet, as with the previous question, but hey, we're going to figure out a bit more as we go along. So f of 0.99, we have 0.99. We're going to take that minus 2 again. We're going to do 0.99. We're going to square it. We're going to plus the 0.99. We're just replacing x with 0.99. That's all we're doing, because that's the value we're inputting into this function here. And fix these up. All right. So we get f of 0.99, fix that one too, is going to be, on our top we have negative 1.01 in the numerator. In the denominator we got negative negative 4, as a matter of fact. There we go, fix that up, negative 4.0299. And these numbers are all just coming from the simplification of the previous component that we had, the previous part over here. We're just simplifying this down to get these two values, numerator and denominator. And then if we do a bit more simplification, we end up getting that our final answer for this component should be 0.25063. So that's great. So we did this. We have our next part. And now we can try f of 1. And if we put 1 in, we get 1 minus 2 all over 1 squared plus 1 minus 6. And this actually does simplify. And it's going to be a bit interesting, because we're going to get negative 1. Guess what's going to be over? It's going to be over negative 4. And this is one of those cases in which the book's actually being a bit nice to us, and they're giving us the answer straight up. We could have just, we could have essentially just put 1 in here and found the answer, because at 1, yes, the function does give us a corresponding y value. It's not unknown. So really this type of question didn't have to be a limit. The textbook just wanted it to be a limit. So this is one of those easy ones in which I would say, if, I doubt that on any test you'll experience something like that, but we got lucky this time in that this value right here that we just got from plugging into the function is actually the limit. So that's a bit of a surprise. That's something that won't happen often, I'll say. So we'll just finish this table out. We'll just grind it out, and we end up getting over here negative 0.99, and this is all over negative 3.9699, and this all in turn simplifies down to a nice value of 0.24938. So there we go. And if we didn't know that we could put 1 in, this value here in conjunction with this one would have really told us that the answer is 1/4. Because if you look, when we're to the left of it, we're basically at 0.25. When we're to the right of it, we're basically at 0.25. Now I'm just going to do, for the sake of it, for the heck of it, I guess, the last one. Might as well, right? So we have f of 1.1. We'll just grind this one out real fast. So we have 1.1, subtract the 2, do 1.1 squared plus 1.1 like this minus 6. Alright, f of 1.1 is going to be, on the numerator we get negative 0.9. That's great. In the denominator we get negative 3.69. So this all nicely simplifies down to 0.24390. So that's great. And with these questions, they're all going to be a bit cumbersome. There's going to be some labor involved, but hey, you know what? We got through it, and we got the right answer. That's really what counts at the end of the day. So, all right, now we're gonna actually move on real quick, and we're gonna do one more of these. I think is all we really need to do. And this one's gonna be a bit different. It's gonna involve some trigonometry. So this is question number 13 that we're actually gonna go to, and this one's gonna be a bit trickier in that there is a bit of trig, and trig can be a bit complicated for some people, but it's a good thing to always go over. So if the limit as x goes to 0 of the sine of 2x all over x, and once again we have the discretion here to make the table, and I'm just going to do it as I did for the previous example that we covered. So what I'm going to do actually is our first value is negative 0.1, our second value is negative 0.01. As you can see, we're just getting closer and closer and closer to 0. I'm going to put 0 in. Then we have I kind of messed this up. My bad, guys. This is supposed to be 0.01, and then we end up getting 0.1. Let me fill that in. Alright, so there we go. So there's our chart. This is really, so this is what we're going to use to hopefully guide our work. So we have f of negative 0.1 that we got to solve. So we have sine of 2 times the negative 0.1 all over negative 0.1. And for these questions, please, please, please remember, in radians. You've got to be in radians for these types of questions. Unless the example specifically tells you to be in degrees, you've got to be in radians. It's the default setting on your calculator. Don't change it. If you have, please change it back, because the answer you're going to get is going to be completely different from mine, and it's going to be wrong. So we got this, and negative 0.1. This all ends up getting us 1.98669. So there's our first part. First piece of the puzzle is solved. Not that hard. Only difference is we're just doing a bit of trig. So then we do this. We got the sine of 2 times negative 0.01 all over negative 0.01. Do a bit of this, and okay, at the numerator again we get negative 0.02000. I am going to say this value isn't exactly this. There is some residue. It's just because I had to round the value at 5 decimal points. You're not going to see the extra numbers that are at the end. All over negative 0.01. So f of negative 0.01 in fact results in an answer of 1.99987. So that's pretty good. My 8's a little weird, but hopefully it's somewhat legible. So there we go. That's great. Now we're going to try f of 1. And this time we're not going to get so lucky. This time the textbook actually made it a bit harder on us. They're not going to let us get away with just being able to put in the value of the function and get an answer. So we're actually going to end up getting the sine of, hold on, my bad, what am I doing? We're trying to look at f of 0. Oopsies. Oops, got a little bit ahead of myself. Trying to look at f of 0. Alright, so we do f of 0, we get the sine of 0, which is 0 over 0, and that's obviously an issue. We can't divide by 0, and so we are looking at a situation like this, or we can call this undefined. Undefined. That's great. So we didn't gain much out of that, but hey, maybe every once in a while teachers are a little nice and they make it that you can just directly input the value in. But now we're going to work from the other way around. We're going to work from the right, and we got 0.01 here, so we get f of 0.01 equals, in our numerator we got a value of 0.02000 all over 0.01. There is residue in the numerator, so don't be surprised when my answer isn't what you expect. It's actually 1.99987. And this is a good answer to get back because we're looking with a sine wave, and so sine waves, obviously, we're going to have instances in which there's going to be little crests and peaks, and so it looks like we are kind of coming over a peak because these two values are the same. So we look to be in good shape. and those values do make sense, so that's always good to know. So here, once again, we got the sine of 2, taking it times 0.1. We're dividing it by 0.1. There we go. Just like that. Not that hard, not that tricky. And we're going to end up getting 0.19867 here in the numerator. And our denominator is a nice 0.1. If we just simplify this a little bit, we're going to end up getting a value of 1.98669. So that's great. We have completed our table. We're all done, and we can pretty much see from these values here, from all these values actually, that the limit as x goes to 0 definitely seems to be 2. So that should be our answer right there, 2. So that's great. So yeah, these definitely numerically, they're not that hard. They're just a bit labor intensive. That's really all they are. So now we're going to move on real quick, and we're going to get into the graphical side of things, which, trust me, it's definitely a bit more exciting. It really is. So our first question I have, we're going to be looking at number 15. And so in number 15, we're looking at the limit as x goes to 3 of 4 minus x, like this. All right. And so what we're doing is they actually are very nice, and they give us a graph that I'm just going to reproduce. Kind of sloppy, but hey, that's okay. So they give us 1, they give us 2, they give us 3, they give us out here at 4, they give us 1, they give us 2, they give us 3, extend this, they give us 4, and they give us just a straight line that goes from here, from 4 to 4, like that, sort of. Probably should have come down more, but that's okay. And we're told we're trying to find the limit at 3, and at 3, we actually are circled in. They give us a hard dot here that lines up with 1. And so just looking at this graphically, we can look back at our definition, and we can just say that if we look to the left and to the right, so if we look to the left, like over here, in this direction, if we look to the right, over here, what we're going to see is that as we get closer and closer here to 3, from the left and from the right, the y values that they have are approaching 1. And so we can say that yes, indeed, a limit exists. So we can say yes, there is a limit. And that limit is in fact going to be at a value of 1. And that's going to be at 1. So there we go. That's pretty easy. That's all you got to do for these. You just gotta look a bit carefully at the graph, and you can figure it out. So now we're going to move on to our next one. And they're going to get a bit trickier. They're going to throw in a couple interesting little things here into the mix, but overall this shouldn't be too hard. These guys should be pretty easy to handle. So we have the limit as x goes to 2 of f of x, and they actually, this is a piecewise function, which makes it a bit interesting, albeit a little complicated and kind of scary, but we can handle it. So we got this, and then we got 0 when x equals 2. So this is basically just saying that we're going to use 4 minus x whenever x is anything but 2, and then when x is 2, f of x is actually going to be 0. So when we graph this one out, they provide us with a graph, just recreating it again. They go from 1, they give us 2, they give us 3, and they give us 4, like this. Then we have 1, 2, 2, I don't know why that didn't write, 3 and 4 up top. And once again, we're going from 4 to 4. It's just a nice straight line. This time I think I'm going to do it kind of. It's a bit ugly, but it's okay. And then actually we have, if we look back, we have at 2, at an x value of 2, we have a circle here at 2, 2, because its function value is down here at 0. So there it is down there. And so we're asking for the limit as x is 2. And so what we're going to do is, once again, we're going to look from the left and to the right as we approach 2. And I drew the arrows backwards last time, unfortunately. But as we look from the left and from the right, we can see that as we get to approaching x value of 2, that, yeah, both sides, they're going to a y value of 2. So we can say definitively here that, yes, there is a limit, once again, And its limit, as x goes to 2 in this case, is a value of 2. So that's great. So that's done. So that one was pretty similar to the last one. The only difference was there's a hole here and the actual function value is down here, but that doesn't matter. We're just looking as we approach from the left and from the right. And as we did approach from the left and from the right, they in both those situations, we were going to our same y value, which was 2. And so that's why the limit is 2. So we're going to do one final one here, the end of the page, and it's question number 19. So it's asking us the limit as x goes to 2 of this little guy over x minus 2. So, whoops, my bad, I messed up. One sec, let me fix this. There wasn't supposed to be any absolute value signs there. That was my bad. So, over x minus 2. Alright, so there we go. So once again, they provide us with a bit of a graph here for us to work with. Just going to reconstruct that like this. Alright, so we have, they give us like 1 and 2 and 3 like this. And then they give us a hash mark here at -1. They tell us this is -2. Go a bit down, they say this is -3. That's great. They give us a hash mark here for 1, a hash mark here for 2. They tell us that this is 3, this is 4, and this is 5. Alright. And then they just put a hash mark here where it's supposed to be -1. And where we draw in what's given to us is that there's a circle here, so there's a hole there. And I have a straight line that goes through -1 to the hole. And then we go back up there, and we have it continue at 1. So we have it at 1 and we have it at -1. And we have this jump here. And we're specifically looking for the limit as x goes to 2. And unfortunately, this jump right here happens at x equals 2. And that's a bit of an issue, because if we are to look from the left over here, so as we're less than 2, if we look at what we're approaching, we are approaching a y value that's staying constant at -1. So on this side, we're looking at -1 over here. But then if we look from the right, so values greater than 2, we're staying constant here at 1. So we are approaching 1. And this is an issue. We have a conflict here. We have 1 here and we have -1 here. And that conflict means that we don't have a limit. We can't definitively say what both of these values are approaching. They're not approaching anything together in any way. And so we have to basically just declare that no, there is not a limit. And that's your final answer right there. This is it. There isn't a limit. There's just not. The function, the nature of the function doesn't allow there to be a limit. So that's our final example here, and hopefully this video is helpful for you if you were having any trouble, or if you just want to get a bit of a refresher at looking at limits from a numerical and graphical standpoint. But this is all the examples I have for now. If anyone would like to see some additional examples from this section, be sure to leave a comment in the comment section below. And if you like the video, give it a like. And hopefully I'll see everyone around next time. Our next video that I'm going to be posting is going to be section 1.3. And in that section we're going to be doing a bit more limits, but we're just going to be looking at evaluating limits from an analytical standpoint. So a bit more complex than this, but really more the same. So once again, thank you for watching, and